Welcome to the 10th lecture for Physics 4C. We start our first modern physics topic in this lecture, special relativity. As this is material that will challenge your intuition about our universe, we will start slow. First, we cover the postulates of special relativity, starting with the first postulate, also known as the principle of relativity. Examining this principle together with the known laws of physics reveals an apparent contradiction, which I call the problem with the speed of light. With the Michelson-Morley Experiment closing a loophole that some people wanted to believe in, a medium for light called luminiferous ether, we are left with the second postulate of special relativity, the constancy of the speed of light in vacuum, which I call the correctness of the Maxwell's theory of electromagnetism. Then, in this video, we explore the first consequence of these postulates. Simultaneity is relative. That is, when we observe two events happening at the same time, this idea of two events, separated by space, happening at the same time, depends on the observer's inertial reference frame. We have two distinct examples of this phenomenon in this lecture video. In our next lecture video this week, we will look at two more concrete applications of the two postulates of special relativity by deriving the formulas for the time dilation and the length contraction. So it falls under the heading of principle of relativity. And it's not actually a new principle. Depending on your instructor, they might have even mentioned it in Physics 4A. And it's something you can actually reason through. What's the quickest way to do it? I can give you the scenario that Galileo thought up. So there's this German phrase, Gedanken experiment, or I don't know if experiment cannot be a German word. I don't know. In English, we call it thought experiment. And all it is trying to visualize or imagine a situation where you are trying to apply the laws of physics. So think of this thought experiment. You are in a submarine, and you are in your bunk bed, and in your room there's no windows outside anywhere. How would you know if the submarine is moving or not? Now, if it's a very bumpy ride, then you will know it's moving. Let's imagine that it's a very smooth ride. Or I guess most of us haven't been on submarine. Imagine you're on an airplane and there's no turbulence, the windows are closed so you can look outside. How would you be able to tell the difference between is the airplane flying versus is it just sitting on the runway with the engines running? Like, how would you be able to tell the difference? Can't really? How many here have been on an airplane? Yeah, so once it's at the cruising altitude, have you walked around? Like, did it feel any different from regular walking around? Not really, right? Yeah, so that's our common experience. And that relates to what's called a principle of relativity. And I guess you could summarize it this way. Laws of physics are the same in all inertial reference frames. I think most people here are familiar with what reference frame is, coordinate system and all that stuff, right? The phrase that I know I skip in my Physics 4A is the phrase inertial. Can someone tell the class what inertial means?
It's from Newton's first law.
I also skipped that. So Newton's first law defines inertial reference frame. Let's describe inertial reference frame without reference to Newton's laws. What's a synonym for inertial?
homogeneous mass.
Not quite homogeneous.
Mass?
Mass? Oh, you're thinking of inertia.
Oh, inertial.
There's L.
Non-accelerating?
Non-accelerating, yeah, that's it. Inertial reference frame is a non-accelerating reference frame. It's quite simple. And in non-accelerating frame, Newton's first law applies. So this is the demo that you might use to illustrate it. So, we actually use this demo in physics 4a for independence of vertical and horizontal motion. And you could say, well, vertical and horizontal motion are independent because this is true. So the laws of physics are arranged in such a way that there's some spring-loaded mechanism here. And when I trip this thing, it launches a ball, right? And I could put this cart in a different inertial reference frame. The inertial reference frame that's moving along with this cart. As long as I'm not pushing it, the frame that's moving with the cart, that's a non-accelerating frame. And so you have already seen how this ball moves in the reference frame of this room, right? And when I push it, you are going to see this ball moving in the reference frame of the room again. And this is what I'm asking you to visualize. Imagine you are an observer riding with a cart. How would you see the ball move? Would you see the ball move in a parabolic arc like this? Or you'll just see it moving up and down, right? So like, if you are sitting in an airplane and throw a ball up, then it just goes up and down back to your hand. But for someone looking at it from outside, it might do that parabolic thing. And in both cases, the ball returns to your hand because of this. Right? It's a fairly basic principle. In fact, it's kind of difficult to imagine this working in the nature working in any other way. Somehow that if you're moving, the laws of physics change, that would make physics actually very challenging. That would make science itself very challenging. So this is where I want to introduce a couple things that seemed to threaten this principle of relativity. Let me start out with the easy example. How fast does sound move?
331 meters per second.
Yeah, let me round it down to 340 meters per second. So speed of sound, let me write it down somewhere. So speed of sound, it's about 340 meters per second at room temperature, 1 atmosphere, et cetera, et cetera, et cetera. So if you could see the sound waves coming out of my mouth, you would see it moving at 340 meters per second. What if this source of sound was on a train? So let's say this is a source of sound, and the sound waves are going in either directions. If the train is stationary, then each of these wave fronts, as you look at it, it's moving at 340 meters per second. 340 meters per second, like that, right? If it stays, train is stationary. Now imagine that the train is moving at some, reasonable speed. Let's say that the train is moving at some speed of, what's a reasonable speed? 40 meters per second? That's like 80 miles per hour. So the train is moving at 40 meters per second. Like if you're standing out here looking at those sound waves, would they still move at 340 meters per second? No, it'll change, right? What does your intuition tell you? As you're observing it out here, what is the speed of sound from out here? Yeah, plus 40 meters per second. So from out here, you would see the wave speed of 380 meters per second for the sound wave that's moving in the same direction as the train. What about the sound wave that's going the other way? You'd be surprised. Like all this is very intuitive. That's why even, well, sorry, I don't mean to sound dismissive. That's why people could figure this out even before time of Newton, before there was laws of physics or something, I don't know. So this would be at 300 meters per second. And in fact, this leads to something called the Doppler effect that we could have covered when we were doing waves, but we kind of skipped. So these changes of speed of sound is what leads to Doppler effect. There are videos on YouTube where people record a fire engine passing by them. As it's coming towards you, the sound, I guess, sounds at higher pitch. Wait, is that right? Yeah, higher pitch, and it's moving away from you. It's at lower pitch, and it's tied to how speed of sound changes as the source is moving. Good. Now, does this fact does that seem contradictory in any way with your sense of principle of relativity? Like the way you guys gave me these answers was intuitive. Principle of relativity is also intuitive, based on everyday intuition. Is there any disagreement between these two? Like, are you okay with the fact that speed of sound in this reference frame, 340 meters per second, and the speed of sound from where I stand are different? Yeah, it's all okay? Yeah, I guess, you know, the way you could, so let me slightly reword this. So given that the laws of physics are the same, supposed to be the same in all reference frames, all inertial reference frames, what makes this inertial reference frame special compared to where I'm standing? That, you know, in this reference frame, you could say speed of sound is 340 no matter what direction it's going, but from where I'm standing, speed of sound changes depending on the direction. Like, what's special about that reference frame?
That one's accelerated, or it's moving at a constant velocity.
It's moving at constant velocity. As it's moving, what else is moving at constant velocity with the train? Well, speed is not a thing. Well, wave is also not a thing, right? Because wave is the disturbance. I want an object that I can say is moving with it. That's that.
Whatever is making the sound.
Okay, the source. So this is something common with all waves, except for one, which we are getting to. The medium for the sound wave is moving along with it. So the medium for the sound wave here is air. And in fact, the number that Javier gave us is specific to the properties of air. If you make the air thinner, denser, then it'll change things. So this is the only reference frame where air is stationary on average. That's why the speed of sound didn't depend on the direction. From out here, the air itself is moving. So this speed of sound, what it is really, it's relative to air. That's why everything that we are describing here intuitively is all consistent. So you make the air move, then speed of sound will sort of add to that movement of air. And you could get the same thing if there's a wind blowing past. Wind will also just throw the sound waves off, of course. Good? Okay. So this is all good. So with since air, or I guess medium for sound wave. So most people didn't have problem with the principle of relativity. It fits with everyday experience. When you are describing things like waves, sound waves, then you can describe how it fits into the principle of relativity by saying that the speed of sound is relative to the medium that the wave is traveling in. So you make the special whatever. Up until late 19th century, late 19th, early 20th century, That's when physicists discovered one wave that does not appear to have a medium. There's one wave that you know of so far that doesn't require a medium to travel. It can travel through vacuum. Light, yeah, electromagnetic wave. So that's the problem with the speed of light. So, so you know what light is? It's an electromagnetic wave, and the wave equations that you saw me halfway drive the first day of class, it was based on Maxwell's equations in vacuum. So there's no medium to speak of whatsoever. And do you remember what the expression for speed of light was? Or C?
1 over square root mu naught epsilon naught.
Yeah. 1 over square root of mu naught epsilon naught, or approximately 3 times 10 to the 8 meters per second. And this expression is problematic. To a physicist who believes in principle of relativity, this expression is a bit problematic. Let me try to sketch the picture why. Imagine you have a train like this. And we will imagine that the train is moving at some speed, and we'll say it's moving fast enough. I'm just going to call its speed v, because I don't know. It's a choice between writing down something that's kind of unintuitively large versus leaving it as a symbol. Let me leave it as a symbol. Train moving at speed v. And let's say you have a source of light. You have a laser pointer or a lamp, something here that's emitting light waves. And if this v is 0, then you know how fast the light wave's moving. It's moving at speed c. Oh, that way. Or here, it's moving at speed c also. Right? So once the train starts moving at speed v, what does your intuition say about the speed of light here? So as you're looking at the light from out here, how fast should the light be moving? Yeah, your intuition says that, well, the source is moving at speed v, so it's the speed of the source plus the speed of the wave. That's how fast it should move. And here, this is how fast it should move. That's what your intuition tells you. And this is where this leads into a bit of a problem. So what you are claiming here is that this is speed of light, right? C plus v speed of light, which means, according to the formula we derived using Maxwell's equation, it must be equal to 1 over square root of mu naught epsilon naught. What are mu naughts and epsilon naughts? They're constants. They are, permeability of free space and permittivity of free space. These are constants that apply to vacuum. And here we had an out. We could say this reference frame is special. This is the reference frame where air is at rest. But you cannot say that this is a reference frame where vacuum is at rest. Vacuum is nothingness. It makes no sense for vacuum to be moving, or so. So that's the problem that you come across. So I guess here's another way to phrase it. So we say laws of physics are the same in all inertial reference frame. Laws of physics, according to Maxwell's equation, determines the speed of light. So if the laws of physics are the same in all reference frames, it must mean that speed of light given by this is the same in all reference frames. That's what it has to mean if principal relativity is correct, and I guess Maxwell's equations are correct. And for us today, it's actually not that difficult for us to say Maxwell's equations are correct. The theory of electrodynamics that we have known for a century and a half is not incorrect. But for the scientists living in the late 19th century, this was a harder jump because it's a recent discovery for them. Even when Einstein published his paper on special relativity, was it 1905? I forget the exact year. So he wasn't born that long after, or was he born? He wasn't born that long after Maxwell came up with his Maxwell's equations and predicted electromagnetic wave. So I just, because we're going to go into a bit of a history about special relativity, I just want you to acknowledge that it was difficult for people at the time to accept this fact that we are going to start out with as one of the postulates of special relativity, that because of principle of relativity, laws of physics are the same in all inertial reference frames, and the laws of electrodynamics are also laws of physics, and laws of electrodynamics are the same in all inertial reference frames. That means one of its consequences, the speed of light, is constant in all inertial reference frames. In physics, we don't, physicists are, let's see, we don't repeat ourselves a lot. You won't really find any physical laws that are that duplicate each other. Like if you have something that's stated as law of physics, in some way we are like mathematicians. If you build an axiomatic system of mathematical system, usually you have an axiom because it's absolutely necessary. You don't have two different axioms that do the same thing. So when in about 30 minutes or so, when we get to postulates of special relativity, the second, what we call second postulate of special relativity is the one physical law that maybe you'll be told that essentially repeats something that you already know. And what it reflects is the hesitation on the part of the 19th century physicists to completely accept the new theory of electrodynamics. And that's the bold assumption that Einstein makes when he comes up with a special theory of relativity. Or theory of special relativity. So, so this picture that we were trying to draw based on our intuition, it's wrong. All of this is just wrong. And we can see that because it's contradictory with other things. And we are going to have to draw up a new picture that's going to be consistent with all the laws of physics, as in how they fit into each other. So let's take the break now, and when we come back, I want to describe an experiment that helped people accept this reality that speed of light is constant in all inertial reference frames. But as we go into that, this is really the maxim I want to leave you with. No one is born with the intuition in special relativity. So as we go through in special relativity, the thing that will make your life easy is if you accept that all of you have wrong intuition. I had wrong intuition until, I don't know, 2007, until about 10 years ago. So no one comes into special relativity having any kind of correct intuition. So if your intuition and your math disagrees, the math is probably right. And the hard work in special relativity is reforming your intuition so that it actually agrees with the reality. And so let me just leave you with that, and we'll go through some of the things that more thought experiments and actual experiments that will help us realize how we have to change our intuition. Yeah. Welcome back. So this is a historical experiment that I want to just describe quickly because it's actually useful setup to consider what's going on with this new reality of nature. So, but to be clear, to be historically correct, Einstein was not influenced by this experiment at all. So when you look up Einstein's work, his original work on special relativity is what he titled Electrodynamics of Moving Bodies. So he was actually interested, he was a theorist. So he was interested in it purely from a theoretical point of view. But what this experiment is good for is for other doubters, other people who doubted that Einstein was correct in assuming that Maxwell was correct, another theorist, that this experiment proves for those other people that Maxwell was correct and Einstein is also correct. So we covered this when we did optics. So I will just go through this quickly without undue wasting of time. So, you know, you have, so Michelson-Morley didn't have laser, but they have some source of light coming in, split it into two parts, combine it back. You can see the interference fringes like this picture here, right? We covered that. And so what Michelson and Morley thought they could do with this interferometer is they thought they could change, they could measure this change in speed of light. And there's an underlying theory behind it. So what some people were doing was they were introducing this mysterious substance called luminiferous ether, whose sole purpose is to serve as a medium for light. This luminiferous meaning light carrying in Latin. So in Latin? I'm pretty sure it's Latin, not Greek. So what Michelson and Morley were trying to measure is they were trying to measure the ether drift, or how fast is Earth moving through ether. So, so let's say, just as a matter of labeling things, let's say ether is drifting this direction. So this is the direction of, I don't know, ether wind. That's how fast this mysterious medium for light is moving. And for all these people who didn't believe in Maxwell, you'd say the Maxwell's laws hold correct in the reference frame where ether is at rest. So speed of light is c, if in the reference frame this ether is stationary. So if ether is moving in one direction with some speed v, then they would say, oh, then in this reference frame, speed of light is faster going that way, and it's slower coming back. You can almost think of this like a current. So you have a boat that has a, I don't know, water speed of 50 meters, that's too high, 20 meters per second, and if it's moving against the current, that from the shore, it'll look slower, and if it's moving with the current, it'll be faster from the shore. That basic idea. So in the simplified of the Michelson-Morley experiment, you would imagine it this way. In your lab frame, you have one light beam that's being sent this way. You have light beam that's sent up, bounces against the mirror, and then comes back. And you have another light that's sent this way, bounces against the mirror, and then comes back. Good? And now what you have to, so I guess for this direction, it's kind of easy to imagine what would be going on if this whole ether idea was correct. You would say going that way, speed of light increases. So going this way, light moves at a speed of c plus v. And then coming back, the light wave is moving against the current. So it's c minus v coming back. Yeah? And this direction is actually a little bit more tricky. So imagine this way. So you are going from, if the light was actually aimed directly at this mirror, would it actually reach the mirror given this presence of ether wind? So how should it be directed? Should it actually be directed at an angle this way, right? So let's say, you know, that's how we directed the light. So the actual direction of light, it kind of goes this way. So and then it strikes it, and then it comes. So I mean, so for a one-way trip, this is the actual distance being traveled. Instead of, so if this apparatus has the arm length of d, let's say they both have the same arm length d on both sides, then on this arm, you would say that the distance traveled is 2d, one way that way and then back. On this side, distance traveled, you have to be a little bit more careful. You're not traveling 2D because it's actually working against the current, so it has to use a component of velocity against the current. Okay? So we can actually derive a quick formula and do a quick estimate to see that Michelson and Morley should have been able to see this ether wind. So this is an example of a null experiment where experimentalists actually saw nothing. So you would think, doesn't that mean they failed? Like, this happens a lot in actually other fields, like in psychology. People hypothesize some effect, you do an experiment, you see nothing, and that doesn't get published because no one's surprised by the fact that nothing happened. But sometimes there's such a heavy expectation for finding something. The fact that you found nothing actually becomes a surprising fact that you have to try to explain in your theory. So let's see. I think the way I can do the calculation is, let's do it in terms of the time difference. And when I plug in the numbers, I will compare the time difference with some, let's say, frequency of light. Because that's going to give you when you are going to get one fringe of difference, right? So I will plug in the numbers in later, but I want to just derive a few formulas first that I need to plug in numbers to. So the two formulas I want to derive is the round trip time for this arm and the round trip time for this arm and the difference between them. Okay? So if velocity is 0, those two round trip times should be the same. But when they're not, they're different. So, okay. So let me call this arm 2, this arm 1. So I think a round trip time for this is easier, so let me do that first. So round trip time T2 is time that takes to get there. So that's d divided, so, speed is length by time, so time is length by speed, right? So distance divided by c plus v, and the trip coming back plus distance divided by c minus v. Okay, so that direction of ether wind means this apparatus is moving this way, so going that way it should take shorter, because this is moving towards the light source. And going back should take longer because the target is moving away. Okay, good. So you have this fairly simple expression. And since it's so simple, let me simplify it a little bit. I can actually combine these two fractions. So, factor out d and combine the two fractions. So it's a d times product of the bottom. Does everyone recognize these two products as being c squared minus v squared? Yes, good. Okay, on the top, it's c minus v plus c plus v. C minus v plus c plus v. So v's cancel, nice. So I have 2c divided by all of this. So let me actually write that out. That's going to be, and then factor out c. Factor out c. Let me write it out this way. It's going to be 2 times d over c times 1 over 1 minus v squared over c squared. Is this correct coming from here? I've done a couple extra algebra for some reason. Good. multiply top and bottom by c, then you should get, c divided by c squared minus v squared, which is what this is with this two. Good? All right, so that's my T2. Let's compare this against T1, time it takes to get there and back. So there I have to know a little bit of, let's see. So I have to know this distance, which is not given to me. But, well, so this distance I could express it as v times t1 divided by 2. That's how long it takes to get there. This is the distance traveled in that much time. All right. Okay, then I think I know this distance, right? It's a Pythagorean theorem, right triangle. This distance is still d. So this distance that the light is traveling in time of, so this travel happens, so when this happens here time is t1 divided by 2, half the amount of time of the whole full round trip. And coming back, it would take the same amount of time, right? Okay, so let's calculate for this time. So I can say this t1 over, let me put it this way. Yeah. So t1 over 2, amount of time it takes, is the distance, which would be square root of d squared plus v times t1 squared, v squared t1 squared over 4, square rooted, divided by the speed. It's moving at speed c. So, c. All right. So this is where, hopefully, if you are observing carefully, you would realize that I'm not done. I have to do a little bit of algebra because I have t1 here and here. I want it solved entirely in terms of t1, in terms of everything else. So I have to do that bit of algebra. So let's just go through and do it. It's not that long of an algebra. So square both sides. Then you get t1 squared over 4 is equal to 1 over c squared times this, no longer square rooted, d squared plus v t1 squared over 4 still. Good. Let me collect like terms of t1. Then you end up with 1 over 4, or let me factor out t1 squared over 4. So t1 squared over 4 times 1 minus 1 over c squared times v squared. So minus v squared over c squared. Good. That's this thing moved over, and the rest are d squared over c squared. Yeah. So move this over to here, take the square root, move the 4 over also. Then you get this result for T2, which is remarkably close to this. T1, sorry. You get this for T1. T1 is equal to 2 times d over c, 2d over c times. And the only difference from this is instead of just being this, 1 over 1 minus v squared over c squared, you have to take the square root of it. So there's a power of 1/2 here. That's the only difference between, label 2 here, between this is T2, between T2 and T1. So let's just plug in some numbers. I want to just plug in some reasonable numbers and see if this kind of experiment can be done to see an interference pattern. So we are talking about remarkably short amount of time, like nanoseconds. So, but I think you will actually see something. So let's try that. Let me use Wolfram alpha because that'll make me not deal with units. So So which one is longer? Is T2 longer or T1 longer? I think T2 is longer. Yeah, so let me do T2 minus T1. So algebraically, that will be 2 times D divided by C times, so 1 over 1 minus V squared over C squared minus square root of 1 over 1 minus V squared over C squared. Good? Okay. I'm going to use a bit of Wolfram language to plug in numbers. There's a syntax called substitution. I'm going to put, what should I put in? What's a reasonable length for Michelson interferometer? 2 meters? So let's say a meter. I'm just doing order of magnitude calculation. 1 meter. C, hopefully it gets it that C is the speed of light. What is a reasonable speed for experiment like this? What do you think Michelson and Morley used for speed of ether wind? So now they were rotating something. They were actually rotating the apparatus. So they would set this up, and then they would rotate it by 90 degrees. Like, what would they be doing? It's not rotate. It does have something to do with Earth, but it's not the spin of the Earth. It's something else. Orbital speed. Yeah, rotation around the sun. That's actually pretty high. Let's just look that up. Orbital speed of Earth. So, that's just some reference number to start out with. 108, well, let's see. Is that in meters per second somewhere? No? Okay. Wait. Wait. Okay, 30 kilometers per second or 30,000 meters per second. Let me put that in. So V would be 30,000 meters per second. So it's actually pretty high. I think that's everything, right? Let's see what we get. So when you put those numbers in, no, so the idea is that, so with the interference, the pattern you get, it doesn't really tell you anything. It's the change in pattern you are looking for. So you set up this apparatus, having it arranged this way, seeing some kind of interference. And as you rotate it, you are looking for that shift in the interference fringes. Good? Yeah. So, but the V that you are using for reference is the speed of Earth around the sun, assuming the ether is stationary around the sun and all that stuff. All right, so let's see. Did they? Okay, they're not putting in a number for C. Let me do a number for C. C is about 3 times 10 to the 8 meters per second. Once again, I'm still using Wolfram language. Okay, 3 times 10 to the 8. All right, so it gets, did I do something wrong? Oh, correct the formulas. 1 meter, 30,000 meters per second. All right, for the time, we get 10 to the minus 17 seconds. That doesn't sound like a lot of time. In fact, that sounds awfully short. Let me try converting it to wavelength, because wavelength is what I have intuition for. So it was 3 times 10 to the minus 17 seconds, right? So wavelength would be, so wavelength is speed of light divided by frequency, or speed of light times the period. So speed of light is 3 times 10 to the 8 meters per second. And for the time, I'm putting it 3 times 10 to the minus 17 seconds. Let's see what that gives us. So about, I should have done this number ahead of time, 9 nanometers. Is that comparable to the wavelength of light? It's getting close, right? So we started out with saying D is equal to 1 meter. Well, I can go from 1 to 10 meters pretty easily. I can fold this up. And in fact, that's what Michelson and Morley did. So when unfolded, the D would work out to be something like something like 10 meters instead of 1 meter. So now this would be, so this is about, let me say, in nanometers. So 90 nanometers, that's about a fifth of the wavelength of visible light. So, what? I don't know. Well, let me just leave it here. Without converting it to nanometers explicitly. Oh, okay, 90 nanometer. So that's about a fifth of the visible wavelength of light. So they weren't quite expecting to see one full cycle. But if this is what I want you to imagine. If you had this interference pattern, and if this pattern shifted by a fifth of a whole cycle, would you be able to see that with a careful observation? Yeah, you would be able to see this edge moving out to a little bit, right? So there's a lot of careful experimental work to be done. But even just checking it visually, no electronic measuring devices, Michelson and Morley had enough sensitivity to be able to see this aether wind coming from orbit of Earth around the sun. And when they did it, they got nothing. And in fact, they were able to put a limit on how fast this V can be. I don't remember the number right now. It was substantially smaller than Earth's orbit around the sun. So a lot of people came up with the theories to explain this null result where you saw nothing. And one of those people is actually Lorentz. So let me end up this or wrap up this particular segment here. So a guy called, let me erase all this algebra that we've done it, so we don't need to see it again. A guy called Lorentz came up with this idea. So he came up with the idea that we now call Lorentz contraction and dilation. So the idea he had was maybe as these objects move around in ether, they change their lengths. So as as ether wind, so as this moves this way, the ether wind changes the length of this arm so that this arm gets shorter. And when he was working it out, he also figured then also the time has to somehow change. I don't forget the details. The conceptual understanding was flawed, but he came up with a mathematical transformation that could explain this null result, how this experimental setup would physically change so that when you do the calculation of these two times, with those changes, you gave 0 time difference. And we will come back to this later today while I'm getting observed. But this is the historical background I want you to be aware of as we go into how Einstein approached this.
So let me get started. Before we got to this point, we talked about the first postulate of special relativity, which one might call the principle of relativity. That is, laws of physics are the same in all inertial reference frames. And you might call this principle of relativity. And it's a really old principle. Galileo is often credited with having realized it with his like a sailor in the underhold of a ship. Could the sailor figure out if the ship is moving or not, if it's a really gentle ride? We talked about that already, so let me just leave that be. Now, this is what we will call first postulate of special relativity. It's special relativity is special over all the theories, laws of physics that you might learn. So especially in contrast to the quantum mechanics that we'll cover soon. Special relativity can be almost mathematically derived. A lot of things in physics, it took a lot of experiments for people to figure out what the laws are. Maxwell's equations in electromagnetism, they were like that. Each equation had to be discovered by someone doing experiments. It's only at the near the very end where Maxwell could discover his Maxwell term in the Ampere's law by theoretical investigation, and the really special and remarkable thing about special relativity is that you can mathematically derive everything in special relativity from these two principles and all the other existing laws of physics. So I gave you the first postulate of special relativity, and the second postulate of special relativity is this. It's let me state it in the way I think it's typically stated. The speed of light in vacuum is always at a constant value that we have given the letter c to. C is approximately 3 times 10 to the 8 meters per second. And I think maybe if we want to emphasize, you might emphasize it this way. It's always at c in all inertial reference frames. One might think that's kind of an odd and specific thing to say, unless you heard about it before from popular science and whatnot. So the way I like to call this, the way to give it a succinct name that I hope people will remember is this name. I like to call this correctness of Maxwell's theory of electrodynamics. Well, I guess that's kind of long. The reason I call it this way is because if you assume that what you learned about electromagnetism in physics 4b is correct, which, why wouldn't you assume that? Then it follows from the first postulate that laws of physics, which contains Maxwell's theory of electrodynamics, laws of physics says light travels at c. This is actually something you can derive from Maxwell's equations. You can derive a wave equation, and that wave equation says the electromagnetic wave has a speed c, or in terms of the constants in the electric and magnetic things in the basic SI unit, it goes as 1 over square root of epsilon naught mu naught. I think that's right. So since this expression falls out of a law of physics, Maxwell's theory of electrodynamics, if Maxwell's theory of electrodynamics is correct, then this must be correct, that speed of light in vacuum is always at c. And I think from our perspective, in the 21st century, it might be kind of odd to say this as an explicit thing. But in Einstein's time, at the turn of the century, beginning of 20th century, Maxwell's theory of electrodynamics was pretty young, I think less than 50 years old. So there were some people who tried to come up with corrections to Maxwell's theory. That's what the whole search for luminiferous ether was about. And Einstein's bold assumption is to assume that this new, less than half century old theory is actually correct, that it can be pushed to limit and it won't break. So those are the two postulates of special relativity. And unlike almost anything else you do in physics, you can build the rest of the theory of special relativity out of these two postulates, like you are, deriving theorems and lemmas and stuff that mathematicians do when they develop like axiomatic set theory. So these postulates, you can almost think of it like axioms of special relativity, except, axioms are more of a mathematical thing, and we physicists prefer the words like postulate and hypothesis and principle. So in principle, you can derive everything in special relativity from these two postulates. So let me do it first application, which is this we are going to discover as relativity of simultaneity. So you're going to hear about a lot of thought experiments or Gedanken experiments, which is describing a setup and assuming that all the laws of physics that we know are correct, including these two postulates of special relativity, and then following its consequences. That's all we mean by thought experiment. It's no more exotic than that. So let me draw this picture for you. So imagine we have a vehicle, a relativistic train that's going to have some stuff set up. Let's just describe it concretely. So it's got some length L. It's how long it is. And it's equipped with a special device. In the middle, or very middle of the train, the device is called a light bulb. Oh, I guess it's not that special. It's just a light bulb. It's a pulsed light bulb. I guess that's what's special about it. You can emit a single pulse, and you can kind of, it emits a pulse of light, and then it travels the way light travels. And it's got two more special devices. There's a detector at the front of the train. I'm going to say train's going to end up moving that way, so this will be the front. Let's call that front F. And at the back of the train, let's call that B. Oh, that's going to be so confusing. Rear, let's call that R. Rear of the train. There are detectors. So when you emit this pulse of light, the detectors at the front and the back can detect when the light has arrived. So when they are functioning, they can measure time at front when the light pulse has hit the front, and the time at the rear when the light pulse has hit the rear of the train. Good. I think all of that hopefully makes sense. So I think if you imagine me lighting this up, emit a pulse, then the way I've set up where this is in the middle, hopefully you have this intuitive sense that by the time light pulses hit those two detectors, these two times, the TF and TR, should be the same. Good. And this is what someone might call simultaneous at the same time, meaning these two values of time are the same. So that's what we are used to experiencing. You can set up experiments in such a way that when you do that experiment, you get simultaneous things. And just to keep with the tradition, we can say that Alice is riding in this train. So Alice is the one who oversees all these experiments and makes sure, the TF is equal to TR. I inspected all the equipment. There's nothing broken, nothing misbehaving. And Alice signs off her name to the fact that, yes, these two are simultaneous. Now we want to imagine that this train is moving at some decent speed, let's say 0.833 c, about 83% of speed of light. Very realistic. And we're going to introduce a new person, Bob, who's not on the train, but he's the station manager. So Bob is standing here outside the train, looking at this train, moving at the speed, 83% of speed of light. And when Alice comes back to Bob saying, I set all this up, I measured the times, they were simultaneous, Bob tells Alice, that's not what I saw. I saw light hitting one end faster than the other end. I think if I'm getting it right, when Bob measures those times, Bob will measure it such that the time that the light hits the rear is earlier than the time that the light hits the front. That's what Bob says. And he says Alice is wrong. So, who's right? Is Bob wrong? Because, he's kind of far away from the equipment. So maybe that's why he didn't see it correctly. By the way, I want to make sure that we draw this distinction between seeing and observing. And watch how I didn't put Alice in the middle of the train, because it really wasn't necessary. So if I'm describing what Alice sees, Alice will actually see what's happening up here. She will see this earlier than what she sees back here. But, Alice is smart. She's not stupid. She's smart. She knows that she's closer to the front than the rear. So she knows that when she sees this event happening before, she knows that, oh, that's happening because I'm closer to it. She knows that when she sees this event happening later, she knows that, yeah, it's because there's a travel time for the signal. That's why I'm seeing that later. So because Alice is smart and aware of light's finite propagation time, she makes those corrections. She corrects it for, okay, the distances and the conclusion that she draws after having made all those corrections. That's what we are going to refer to as observing. So whenever we are using the word observing, what we are saying is that all those tiny little minor, really trivial corrections have been made. And what remains is a true, real relativistic effect. So where Alice is, where Bob is, it actually doesn't really matter. The only thing that matters is what reference frame they are in. So let's try to describe what's happening here from Bob's reference frame. So the way this is drawn, the train appears stationary. So let's actually, make a copy of it down here and redraw it so that we can draw it from Bob's perspective with the train moving. So let's break it up into a few snapshots. So there's that moment in time, and I guess we don't really need Alice, so let me not draw her. Trying to draw fewer things. So there's this snapshot that's drawn is the moment in which the light was emitted. Okay, the train moving forward at 83% of speed of light, it'll be moving forward, and let me draw in green where the train will be at some point later. Let's say in the amount of time that light travels to, not quite here, but in the amount of time light travels to somewhere here, about halfway, and somewhere there, about halfway, train has moved. And the train will have moved, I think, I'm trying to draw it to scale. Maybe something around here, it'll have moved to position like this, from snapshot 1 to 2. This will be the position of the train in snapshot 2. You can see that between this 2 and the next equal sized time interval, the light will hit the train, the rear of the train. Let's mark the location here. There will be an event, detection of this light pulse at the rear of the train. And let me label the time there with not TR because I think that gets confusing. Let me prime it so that it's a different symbol for a different number, potentially. Now, while that's happening, I think in the snapshot 3, in about equal amount of time, the light has traveled to here. Front of the train keeps moving. Let me draw that in purple. So in that equal size time interval, the front of the train will have went something like this. So, in snapshot 3, the light hasn't quite hit it yet. So it'll take, snapshot 4, 5. At some much later time is where the front of the train finally gets hit by the light pulse. And now you register the time, T front. I'm not drawing this to scale. But from the description, you can kind of see why Bob would say what he said. That when he observed these two events of the light hitting the back of the train and the front of the train, that the event of the light hitting the back of the train occurred at an earlier time than the light hitting the front of the train. It's a quite strange and counterintuitive effect. I think we are used to thinking of an absolute time. We are used to thinking that if we have something that is simultaneous, we are used to thinking, assuming, presuming that simultaneity is universal. That if something was simultaneous for Alice, that it must be simultaneous for Bob. What we are seeing in this application of the principles of postulates of special relativity is, and I don't think I have even explicitly invoked any actual postulate of special relativity. Other than that, light is traveling at speed of c. And I guess, so I didn't explicitly invoke it, but if you're dealing with sound waves, for example, the way you would resolve this apparent contradiction is to say, oh, that's because so in Alice's frame, these two waves are traveling at the same speed. But in Bob's frame, you would say, oh, they are not traveling at the same speed. The one that's moving towards the front of the train, it moves at the speed of its own speed plus whatever speed the train is moving. And the one that's moving backward, it's moving at whatever its own speed is minus the speed of the train. Like for sound waves, that's how you would resolve it, and you would say that the event of arriving at the back and arriving at the front, they happen at the same time. So in the classical mechanics description, simultaneity is universal still. And what we are saying is that even though this is how we would handle things in a natural, intuitive way, what we are going to say from here on as we venture into special relativity is we are going to say explicitly that we don't trust our intuition. What we trust in is the postulates of special relativity. These are the absolutely true statements that are never wrong, even when they sound wrong. So even though the statement that the speed of light is always c in all inertial reference frames, it'll sound wrong to you until you get used to it, because you will want to correct the speed of the light. And what I ask you to do as a competent, good mathematician is to say, ignore this impulse, hold on to your axioms, say that what is true is the second postulate of special relativity. Light always travels at speed of c, even when you don't want to say that's true. So under that assumption, what I said is, light hits the back of the rear of the train before it'll hit the front of the train, because the light going towards the front of the train isn't moving any faster from Bob's reference frame. It's still moving at c. Light going to the rear of the train is not any slower. It's also moving at c. Now, they are different in other ways, and the way they will be different they'll be different in frequency. That's what will lead to something called the Doppler effect that we'll, I think, look at in later, maybe next week or the week after. So they are different in some other aspects. Their frequency can change, their wavelength can change, but what doesn't change is their speed of light. So yeah, what Bob observes of these two events is that they are not simultaneous. And this is what leads us to say simultaneity. So, whenever two events appear to happen at the same time, that's what we call simultaneity. Simultaneity is relative. Meaning, if you have two events that is simultaneous in one inertial reference frame, like a TF and TR was here, then it's, especially if they are separated in space, then it is possible to find another reference frame where they are not simultaneous. And I believe, especially in lower division textbooks, this fact is not given enough emphasis. And that leads to a lot of confusions in like special relativity paradoxes, that some of which we'll see next week. So I wanted to cite this textbook that I like really a lot. I brought a screenshot here so that I can refer to it in this lecture. This is a screenshot from a digital version of a textbook called Revolutions in 20th Century Physics by a really popular upper division textbook author, David Griffiths. And this particular textbook is actually not written for upper division content. It's written for physics for humanities majors. But I think it's worth reading even for engineering or future physics majors, because there are certain insights that's so succinctly summarized that as a lot of students are going through this physics first class will miss unless they take care to pay attention to it. It's this paragraph that I want to refer to. Relativity has nothing to do with what you observe, or relativity has to do with what you observe in the sense that we are talking about, not what you see with all the spurious effects. We are talking about real effects, not appearances. And it's this sentence I want to bring your attention to. Einstein liked to say that all the conceptual difficulties of special relativity derive ultimately from the relativity of simultaneity. And as we explore relativistic paradoxes, you will see how many I hope you will be surprised by how many of the paradoxes do ultimately get resolved by correct understanding of simultaneity.
So maybe this will be illustrative. So let me try to set this side by side, and I want you to just think through and understanding that you haven't had much time to think about special relativity beyond just learning that just now maybe that second postulate of special relativity says that light always travels at speed c. Um, See if what this Errata submission is trying to say is something that you would have agreed with. So this submission is referring to this picture here, and I guess it might be worth the time to for me to just read through. Well, actually, read through the whole section. So let me do that. Well, whole section. Yeah, let me read through the whole section. I think I can do that in about 10 minutes and it'll be worth the time. So this is section 5.2. It says, so starting from here, do time intervals depend on who observes them? Intuitively, it seems that the time for a process, such as the elapsed time for a foot race, should be the same for all observers. In everyday experiences, disagreements over elapsed time have to do with the accuracy of measuring time. No one would be likely to argue that the actual time interval was different for the moving runner and for the stationary clock displayed. Carefully considering just how time is measured, however, shows that elapsed time does depend on the relative motion of an observer with respect to the process being measured. And I want to make this a little bit more broader. It's not about elapsed time alone. It's about simultaneity, as the section says, relativity of simultaneity. And we'll get to that. Consider how we measure elapsed time. If we use a stopwatch, for example, how do we know when to start and to stop the watch? One method is to use the arrival of light from the event. For example, if you're in a moving car and observe the light arriving from a traffic signal changing from green to red, you know it's time to step on the brake pedal. The timing is more accurate if some sort of electronic detection is used, avoiding human reaction times and other complications. Um, okay, let me just move on. I'll bring that point on later. There's something I want to mention, but next week might be a better time to bring it up. In the lecture, you will see that there's a distinction between what I call seeing and what I call observing in this class. Now, suppose two observers use this method to measure the time interval between two flashes of light from flash lamps that are a distance apart. On observer A is seated midway on a rail car with two flash lamps at opposite sides equidistant from her. A pulse of light is emitted from each flash lamp and moves toward observer A, shown in frame A of the figure. The rail car is moving rapidly in the direction indicated by the velocity vector in the diagram. On observer B, standing on the platform, is facing the rail car as it passes and observes both flashes of light reach him simultaneously, as shown in frame C. So here he sees both flashes simultaneously. He measures the distances from where he saw the pulses originate, finds them equal distance, and concludes that the pulses were emitted simultaneously. However,
Because of observer A's motion, the pulse from the right of the rail car, from the direction the car is moving, reaches her, observer A, before the pulse from left, as shown in frame B. So the light was emitted here, it traveled some distance. Light was emitted here, it travels some distance. In that time that the light travels that some distance, observer A moved towards the right side light. And the light from right side reaches her before the right light from the left side. She also measures the distances from within her frame of reference. She's at the midpoint between the two, finds them equal, and concludes that the pulses were not emitted simultaneously. So far, so good. The two observers reach conflicting conclusions about whether the two events at well-separated locations were simultaneous. Both frames of reference are valid, and both conclusions are valid. Conclusion 1 being observer B says they were simultaneous, and conclusion 2 being observer A says they were not simultaneous. Whether two events at separate locations are simultaneous depends on the motion of the observer relative to the locations of the events. Here, the relative velocity between the observers affects whether two events distance apart are observed to be simultaneous. Simultaneity is not absolute. We might have guessed incorrectly that if light is emitted simultaneously, then two observers halfway between the sources would see the flash simultaneously. But careful analysis shows that this cannot be the case if the speed of light is the same in all inertial frames. And we might analyze this in more depth in a bit after we go over this. This type of a thought experiment, in German, Gedanken experiment, shows that seemingly obvious conclusions must be changed to agree with the postulates of relativity. The validity of thought experiments can only be determined by actual observation, and careful experiments have repeatedly confirmed Einstein's theory of relativity. And this is what I mean that the second postulate is true. It's been repeatedly tested, and the conclusions that follow from second postulate has been confirmed over and over again, which is the basis on which we say second postulate is true. Now, I hope when you heard me read through this section that most of it made sense. Now, let me read this errata, which I'm telling you ahead of time is wrong. So, so with that caution, see if you can spot the point at which this is wrong. So this is what someone who is, usually people submitting errata are physics instructors. So I don't know who wrote this, but I'm assuming he or she was a physics instructor. So this is what someone also who is experienced in physics are saying. The section that describes how observer A perceives the two flashes of light. Observer A will see both flashes of light from the right and the left arrive simultaneously rather than the right before the left as described in the text. This is because observer A is in an inertial frame of reference, and thus she is entitled to say that she is at rest and the platform is moving. So in her inertial frame, she and the two sources of light are at rest, and thus light from both sources would reach her at the same time. If the light from both sources did not reach her at the same time, she would be able to tell that she is the one who is moving, and this will contradict the first postulate of special relativity that the laws of physics are the same for all inertial frames. Observer B, however, would see that the light from the right reach observer A first, because she is moving towards the light, and thus, as perceived by observer B, the two flashes of light will not reach observer A simultaneously. I think you can actually see something that's within the within this description here, that's internally inconsistent, because whether these two lights arrive at the observer A at the same time or not, that's an unchangeable fact. So if these two flashes of light arrive at observer A at the same time in her reference frame, then that particular fact would be the same regardless of what other reference frame you are in. So this second part is just contradictory to the first part. If observer A sees these two lights at the at the same time, then observer B should also observe that these two flashes of light arrive at observer A at the same time. So, so ignoring that second half, which is kind of easy to disprove based on logic alone, if you were reading here and didn't have me to tell you that this is erroneous, where is this Errata submitter wrong? What mistake did they make? I want you to think it through for a bit, and I'll tell you. And this happens quite commonly when people make mistakes regarding relativity of simultaneity. In fact, the textbook encourages probably too strong a word. Textbook description doesn't prevent this kind of mistakes here. So this is the textbook description of these events. So textbook says, now suppose two observers use this method to measure the time interval. An observer A is seated midway. Here it is. A pulse of light is emitted from each flash lamp and moves toward observer A, shown in frame A of the figure. That's all it says. And I think this is the place where if you're writing written words on a textbook, it takes a finesse to one, not mislead and be accurate. So in the textbook, they were careful not to specify in what reference frame these flashes were simultaneous. I think the way A is drawn encourages people to think that they were set up to be simultaneous in observer A's frame. And I think that's why mistake like this can be easily made, even by people who are educated in physics. Because once you start from the mindset these were simultaneous in observer A's frame, then this is the only consistent thing. And so in the textbook, they try to describe how these pulses were not set up to be simultaneous in observer A's frame. They were instead set up to be simultaneous in observer B's frame. So if you want to be more clear, then you can even describe a kind of a triggering mechanism. Maybe there's a kind of a triggering device here. You measure them ahead of time so that you make sure these endpoints will pass those two triggering points at the same time. And as they do, you trigger them. And the important thing here in special relativity, whenever you say at the same time, you have to specify the reference frame. So in this textbook description, they didn't quite describe in detail how these will be triggered simultaneously in observer B's frame. But you can think of a contraption that would do that. And so having been set up to flashes simultaneously in this frame. That's what they did. And whether these lamps were moving with the train or not, that's not quite relevant. Although I guess because they are moving with the train, if you wanted to set up a contraption for triggering these simultaneously in the train's reference frame, that is actually easier than triggering them simultaneously in the observer B's reference frame. In fact, that's what I'm describing in the lecture here. This setup is something that can be used to trigger these two lamps simultaneously in the train's reference frame. And what you see here described is that once you've set up that way, set it up so that this light pulse will reach A and B simultaneously, then what you will find is that working through this here and applying the second postulate of, I guess I kind of describe it around here also. So in the reference frame of the guy who is on the train station, the light pulse that reaches the back end of the train, that reaches it before the light pulse that reaches the front end of the train. So, so once you set up on a set of events to be simultaneous, or a pair of events to be simultaneous, you have to pick a reference frame in which they can be simultaneous in. And I think with the tools we are introducing this week, if this is leaving you maybe confused, I think I would rather you be confused than to not fully absorb the fact that simultaneity is not an absolute thing in special relativity. That whether two events are simultaneous or not, it depends on what reference frame you observe them in. And so the way it's set up in this lecture here, I set up the events A and B to be simultaneous in the reference frame of the train. Therefore, when you observe it in a frame that's moving relative to the frame, then they are no longer simultaneous. In this textbook section, without describing in detail how they would do that, they set it up so that these two flashes would occur simultaneously in this reference frame. Having set it up that way, they are not simultaneous in observer A's reference frame. I think all of this is so I guess I think that as clearly as I can describe it at the moment. Maybe let me end this with more of a foreshadowing for next week, when we'll have a much less confusing analytical tool that will help us both diagram this and describe it very accurately with not as much room for misunderstanding or ambiguity or anything like that. To me, the moment when special relativity made sense was when I learned to use something called a space-time diagram. And it's a tool that is introduced in your textbook. I forget which section exactly. It might be section 5.5. You will see me use this tool of space-time diagram much more extensively than your textbook does. This is an example of space-time diagram, but I don't think that's quite yeah. So this is so section 5.5, which we cover next week, is where you will see space-time diagram illustrated and used in the textbook. So this is where they use it to explain the twin paradox. And yeah, this is the picture I love. And this is illustrating this is illustrating how something called the Lorentz transformation, which describes the transformation of space-time coordinates in a way consistent with two postulates of special relativity, how the coordinates transform under that Lorentz transformation. And and I think, yeah, so they talk about simultaneity here, and with this graphical tool, you can see more easily how simultaneity is relative. Yeah, in fact, this is exactly the picture. So, so you know, if this discussion of, so I think if this discussion of relativity of simultaneity is leaving you feeling confused, I think that's fine. As far as what we are doing this week, I would much rather that you acknowledge, I would much rather that you take this time to unlearn something that you've learned unconscious or subconsciously until now, which is that the idea of something happening at the same time is not something that requires a specification of reference frames and coordinates. That's what we've been doing up until now. And I want you to unlearn that. That whenever someone says things like at the same time or simultaneous, that's a phrase that requires a definition of coordinate system. As much as if I describe something as being along the x-axis, then you would want to know how I'm defining my x-axis. And those axes that need to be defined, and they obey certain kind of geometric properties that is described here. It's these axes that you see described there, and this is a subsection within section 5.5 where you will see that description of simultaneity. So what this is showing here is that this left and the right flash, they were set up to be simultaneous in this coordinate system, x and so in this coordinate system that's described as our resting frame, that would be the frame of this guy, observer B, and the reference frame of observer A, it's described with an axis that looks like this, x prime and ct prime. These axes have rotated, and this lines that are parallel to the x prime axis, that's where time has the same value. So these are the set of points that are simultaneous with this event in the reference frame of the train. And these are the set of points that are simultaneous um, with the right flash in the reference frame of the train. And looking at this, what you see is that the right flash does occur before the left flash does. This is more negative time than the left flash. So this is something we'll go in more detail next week after we have fully introduced the tools that that we can use to clearly lay this out. And um, and in the meantime, for this week, where I want to leave you at is unlearning some of the classical intuitions that you've been relying on so far. Because place where it really trips up even the people who are experienced in physics is the relativity of simultaneity. I think it usually trips you up when you have assumed the simultaneity implicitly. And you will see that in some examples of paradoxes we'll go over either next week or the week after. So